The results that I would like to present to you, it's born by our curiosity. In the past, we worked in a lot of iron-based material, which we have galvanized by using the traditional hot-dip galvanizing. We worked on the galvanizing on low carbon steel, medium, high steel, low alloying steel. Our curiosity is what happens when we use the traditional optic galvanizing on the traditional ductile cast irons. It is born because ductile cast iron is an interesting material characterized by good mechanical properties, and its resistance against corrosion is not so good. And optic galvanizing is one of the most important processing techniques to protect metallic material against corrosion in many aggressive environments. So, a few words about the formation of coating. This is the equilibrium diagram of iron and zinc. We can see the presence of a lot of stable phases characterized by high contents of zinc. You can see it is positioned the capital gamma, 1, 2, and so on. All these phases are always named as capital lambda phases. And then we have delta phase characterized by a good contents of iron, and eta phase, and this is the phase with the very short contents of iron. The process is the same used in traditional galvanizing. Firstly, it is necessary to clean the surface, eliminating all the impurity as oxide with using acid solution as chloride solution or sulfuric chloride solution. And then we have to flux the surface. This way we use a double salt of ammonium chloride and zinc chloride salt on the surface in order to protect during the immersion of the specimen in hot-dip galvanizing, in order to avoid the water oxidation at high temperature due to high temperature of melt. And then we use a cooling in air, simple in air. This is a traditional batch process. So, the importance of silicon contained in the substrate, iron-based substrate, is most important. This is the mechanism of formation of coating and the influence of silicon contents on the surface. Firstly, the silicon promotes the formation of delta phase rich in iron, and this phase is the capital gamma, as we know in the stable diagram, but this is very brittle. It's very easy to propagate and dissolve this phase in delta phase. It is promote the formation of coatings from the substrate to outer surface. This is the section of a traditional of galvanizing. This is the different phase which characterizes the coating. This black is very thin. This is the capital lambda phase. This is the delta phase. Zeta phase is characterized by a columnar morphology. In the outer zone, we have the eta phase, which is characterized by the chemical composition of plastic. So this is the aim of our work. We consider 5 different dipping times in order to evaluate the kinetics of coating formation, and then we use a bending test in order to characterize the damage of the substrate phase. And we use a light optical microscope separation in order to observe the morphology of the image, in order to quantify this damage, assuming a number of cracks, radial cracks, for each millimeter of the forward arc as a damage parameter. The chemical composition of ductile cast irons used to galvanizing is this. You can see the content of silicon is very high, 2.72% of silicon. It's very, very high. And the hypersandling behavior is obtained for 0.125% of silicon. It means that the reaction which are responsible for the coating formation are very, very strong, very developed. And then we have other components. Carbon is wide, but the contents of carbon is mainly inside the nodular phase. This is a ductile cast iron characterized by nodular phase inside the metallic matrix. And the matrix is the chemical composition of matrix is quite similar to a medium carbon steel. This is the device used for bending test. It's not a standard device. It's just a tool developed in our laboratory, which allow us to perform a bending test also on a very short specimen, because in laboratory we haven't a big furnace in order to galvanize big specimen. We work with a sample, very, very short samples. But is this very, the accuracy is very, very high. So this is the situation of cross-section of our galvanized specimen. We can see the presence of graphite nodules in the matrix. This is the coating, and inside the coating we have the presence of the graphite. We think this is due through a diffusion of carbon inside the coating. It is confirmed by this picture. This is a section taken high dipping time, where the dimension of this nodule is very high to respect the dimension of nodule presence in the ductile cast iron. In this case, the dipping time it was about 900 seconds. It's very, very high. Considering the thicknesses of in the metallic phase, we can see the values reported in this picture. For low time, this is about 15 seconds. It's very, very quick process. The dimension of coating is very high. It's an order of 100 micrometer. This value is obtained in traditional steels for dipping time very, very long, about an half an hour. We have the same results for 15 seconds. This is due to high presence of silicon. And then we have explored other dipping time as 1 minute, 3 minutes. This is 5 minutes and a quarter of hour. other intermetallic phase was quite little compared to the wall thickness of specimen, and the main phase is the zeta phase, which characterizes the big percentage of the thickness. Considering bending test, you can see the stronger results obtained for the specimen galvanizing at 900 seconds of time. This is due to the big thickness of specimen. It's about 1/2 of millimeter. You can see the red dot reporting these pictures. In terms of damage, we can see the presence of radial crack. Radial crack sometimes starts from matrix and delta phase interface, but we have the presence of outer crack, which starts inside the matrix, corresponding to the graphite nodules. This behavior is not present in traditional stainless steel, because we have the presence of graphite. Considering the damage adopted, the damage parameter, number of radial crack per millimeter of the former crack, we can see this behavior. In order to analyze the stronger phase, we can see the zeta phase is the phase characterized by low values of damage if compared to the delta phase. Delta phase is the phase which we have to minimize in terms of thickness because it's not so stronger. It is important to underline that the damage is present inside of coating. The surface, the outer surface in this direction is not visible for the external check. This is a problem because if we use the things of machine or components on subjected to deformation, we can have a damage of coating inside. It is not so easy to check this kind of damage. So this is the conclusion. We summarize that we saw in this work. We use the different time in order to evaluate the kinetical deformation. The kinetical deformation coating is very, very high because the presence of silicon is quite. The bending test confirmed that we have a stronger behavior for 900 seconds dipping time. And this is due to the high values of thickness. And the same long observation shows the presence of crack inside of coating, which interests mainly the brittle phases, delta and zeta, characterized by high values of high contents of iron in terms of chemical composition. Thank you very much for your attention.